pulls mechanical levers to operate a hydraulic control system. But on the A330, this heavyweight gear is replaced by an electronic system called fly-by-wire. The pilot tells the flight computer what he wants to do, but it is the computer that translates this intention into action and executes the maneuver.
So if I want to go to the left, stick to the left. Round to the left.
The flight computer adjusts the control surfaces and the aircraft turns left. Maneuvers like this cause the A330 to lose altitude. So the advanced computer compensates by increasing power and pitching the nose up to provide the right amount of lift. The pilot does nothing.
I take my hand, vertical speed 0, 25 degrees.
Command that endangers the safety of the aircraft.
If the pilot were to lose control. Vertical speed 0. The pilot lose control. Information leveling. Quick gears left, 6 left. Right left.
Typically, ARINC429 allows for two standard transmission rates, one at 12.5 kHz and the other at 100 kHz. There are basically two methods, either through a FIFO or using our advanced scheduler, and you can actually use a combination of both. FIFOs are commonly used in software to send messages in a particular order. The UEI 429 I/O board provides you with a 256-word output FIFO. There are actually two modes to the FIFO, paste and non-paste. Paste allows you to control the intermessage timing by using a user-defined clock. Without paste mode, your application simply controls the timing of the transmission. In computing, scheduling is used to coordinate work by using resources other than your application program. The UEI 429 scheduler includes a table that allows up to 256 labels per channel. This scheduler can be started by your application or automatically based on the receipt of a specific label. The UEI scheduler allows you to send multiple messages at different rates per message. Department of Defense. First employed in the F-16 fighter, it has since become a widely adopted data bus used in a variety of military and civilian applications for flight, land, sea, and even in space. Why is Avionics buses? The goal of 1553 is to move data reliably. 1553 messages consist of up to 32 16-bit words. There are three provable design and redundancy for safety. The bus consists of two sides, commonly labeled A and B. If a reply does not come back in a fixed amount of time from side A, the command is sent to the other side of the bus, side B. If we actually take a look at the signal on the bus, looking at the lower two lines, you'll see the bits are half high and half low. This is known as Manchester differential encoding. All this adds up to an avionics bus renowned for its simplicity and its reliability. The only component in the 1553 system that controls all data transfers is the bus controller, which is tied to the mission computer. It has dual buses for redundancy and safety, side A and B, and a fixed response time for all replies. ARINC664 Part 7 meets these needs by using Ethernet technology and commercial off-the-shelf components to address the next generation of aircraft requirements. These requirements include high-speed, deterministic, full duplex, redundant, switched, and profiled networks. The ARINC664 I/O board is designed to work with the AFDX standard. It works on 2 buses, A and B, and manages all of the integrity checking and redundancy management for you. It supports sampling periodic, queuing, and SAP ports. Using its async events, it's also a very efficient AFDX bus monitor. Almost all parts of the I/O board are software configurable and can easily be configured from an XML file. This simplifies the configuration of many ports, but can also be used to program ports one by one for fine-grained control.
Didn't expect that. Mit einem Schräglage findet die Gäste vor allem wohlwollend. Da rutschen natürlich die Kaffeetassen auf die Seite und hängen dann in den Seilen. Aber das sind die Grenzen, meine Hörer. Damit wird einmal bewiesen, mit wie viel Technik.
Running large industrial networks requires high reliability and robust communication. The network's topology plays an important role in how well networks perform in a factory environment. Relying solely on star topologies can be robust but expensive. Having long linear segments can be cost-effective, but at the risk of reducing reliability. Relying on a single network path can bring problems much like those you might encounter driving on your commute home. Imagine you're driving on a highway with few exits and there's suddenly an accident. Not only are you stuck, but you don't know how far away you are from the accident. You could be stuck for minutes or hours. The same thing happens with networks. If a single cable or device fails in a daisy chain, you lose service and it becomes difficult, if not impossible, for data to move around. Now imagine how much easier it would be if there was a traffic cop with sign directing you to an alternate route. You and your fellow travelers arrive at your destination with minimal delay. That's why you need to implement a network with a ring topology. By using a ring topology with the device-level ring protocol, there's always an alternative path for data to arrive at its destination. And with the device-level ring protocol, or DLR, there's a traffic cop, known as a ring supervisor, who directs traffic and keeps data from going in circles. When there's a problem, like a bad cable, the supervisor detects the issue and directs traffic down the alternate path. Further, even while business is running as usual, a ring topology allows you to switch out cables or devices. When the supervisor sees you fix the cable or the device, it resumes normal operation of the ring.